Now there is this one very important theorem in limits with which we can solve a wide variety of problems which otherwise would have been very difficult to solve. And this theorem is called as the sandwich theorem. Or we call this as squeeze play theorem. Squeeze play theorem. This theorem says if we have three functions, say gx, fx and hx, such that gx is less than equal to fx and fx is less than equal to hx for all x in deleted neighborhood of a, such that limit x tends to a gx is equal to limit x tends to a hx and it is equal to L, then value of this limit x tends to a fx, it will also be L. So if we have three functions fx, gx and hx such that fx is sandwiched between gx and hx in the deleted neighborhood of a, that is in the neighborhood of a except possibly at a, such that this limit for this function at a, it is L, and limit of this function hx is also L, then this sandwich theorem or squeeze play theorem says value of this limit of this function fx will also be L. So if we look at this graphically, then suppose we have this function which is say hx, and then we have this function which is gx, and we have this function fx such that gx is always less than equal to fx is always less than equal to hx in this deleted neighborhood of a except possibly at a, then if both hx and gx they approach L, then this fx will also approach L. So if this limit x tends to a gx, it is L, and this limit x tends to a hx, it is also L, then this limit x tends to a fx will also be L. Now using sandwich theorem, we'll prove our very first standard limit, and which is this limit x tends to 0 sin x upon x, it is 1 if it is 0 upon 0 form. Now for this what we'll do is we'll take portion of a circle whose radius is 1 unit. So we have this circle whose radius is 1 unit. Now we'll draw an angle theta. So this angle, it is theta. Now this point is say P and this is Q. Now from this P, we drop a perpendicular and we'll draw a tangent at P which intersects this x-axis at this point say T. So we have suppose PQ, R and S. Now this length is 1, this length is 1, and this is the arc length. Theta is L by R. So this PQ, its length is theta. Now we'll write three areas. Now this first area is area of triangle OPQ. Now this triangle base is OQ, which is 1, and perpendicular is PR, which is sine theta. So this area, it will be 1 by 2 into 1 into sine theta. So it will be simply sine theta by 2. Secondly, we'll write area of this sector OPQ. So area of this sector OPQ. Now previously we have worked out area of this triangle. Now we are working out area of this sector OPQ. Now area of sector is half r square theta. So it will be 1 by 2 r square into theta. So it will be theta by 2. And first one is sin theta by 2. And for this third one, we write area of this triangle OQS. Area of triangle OQS, it will be 1 by 2 into 1 into tan theta. So it will be simply tan theta by 2. Now, if we look at these three areas, this first area is area of this triangle, which is less than area of this sector, which is less than area of triangle OQS. So from here we can write sin theta by 2, it will be less than or equal to theta by 2 and will be less than or equal to tan theta by 2. Now we can cancel this 2 with 2. Now we divide everything with, we can write 1 is less than equal to theta upon sin theta and will be less than secant theta. Now we'll take this limit, theta tends to 0. So it will be this limit, theta tends to 0, 1 is less than equal to this limit, theta tends to 0, theta upon sin theta and will be less than this limit, theta tends to 0, secant theta. Now value of secant 0 is 1 and value of this limit is also 1. Then from sandwich theorem we can say this limit theta tends to 0, theta upon sin theta, it is 1, or we can write this limit theta tends to 0, sin theta upon theta, it is 1 if it is 0 upon 0 form. Now here the question is, let f be a positive increasing function with limits x tends to infinite f3x upon fx equals 1. We need to find this limit x tends to infinite f2x upon fx. Now since fx is positive increasing function, then we know that fx will be less than f2x and will be less than f3x. Now we divide everything with fx, we can write 1 is less than f2x upon fx and will be less than f3x upon fx. Now if we take this limit x tends to infinite, this is 1 and in the question it is given that this limit is also 1. Then from sandwich theorem we can say that this limit x tends to infinite f2x upon fx will also be 1 and that's your option 4. Now here the question is, we are given that limit x tends to 0 positive x into this summation greatest real function of r by x, where r varies from 1 to 15. Now we know that any greater function, it is less than equal to x but greater than x minus 1. So we can write this greater function of r by x will be greater than r by x minus 1 will be less than equal to r by x. Now if we multiply it with x, we can write r minus x will be less than x into r by x and will be less than or equal to r. Now we'll take this summation, r varies from 1 to 15. Now this is n plus 1 by 2 minus 15x and will be this summation r varies from 1 by 15 x into greatest function of r by x and will be less than equal to 15 by 8. Now if we take this limit x tends to 0, this is 120. This also is 120. Then from sandwich theorem we can say that this limit is equal to 120, and that's your option C. Now here the question is, we are given this function f defined from r to 0 to infinite such that fx plus e to the power x plus x square upon fx, it is less than equal to e to the power x plus e to the power x square for all x greater than 0. Now since fx is positive, we can rearrange this inequality as f square x minus e to the power x plus e to the power x square fx and plus e to the power x into e to the power x square. It should be less than equal to 0. Now we can factorize this as fx minus e to the power x into fx minus e to the power x square, and will be less than equal to 0. So from here we can write this fx, it belongs to this interval e to the power x and e to the power x square. Now whatever may be the order, if we take this limit x tends to 1, this limit is e and this limit is also e, then from sandwich theorem we can say this limit x tends to 1 fx, it is e, and that's your option C. Now here we need to find this limit 1 upon under root n square plus 1 upon under root n square plus 1 up to 1 upon under root n square plus 2n. Now for this limit we know that under root of n square will be less than under root of n square plus r, and will be less than or equal to under root of n square plus 2n, where value of r varies from 1 to 2n. Now if we take its reciprocal, then we can write 1 upon under root of n square plus 2n will be less than or equal to 1 upon under root of n square plus r, and will be less than 1 upon under root of n square. Now we take this summation, r varies from 1 to 2n, will be this 2n upon under root of n square plus 2n will be less than this summation, r varies from 1 to 2n, 1 upon under root of n square plus r, and will be less than 2n upon under root of n square. Now we take this limit n tends to infinite. Now here highest power is 1 and here also highest power is 1. So this left hand side limit is 2. On the right hand side limit is 2. So value of this limit, which is actually the given limit, it will also be 2 using sandwich theorem. So answer to this question is option D. Now this third question is, if fx is a polynomial function such that f alpha square plus f dash alpha square equals 0. Now assuming that it is a polynomial function with real coefficients, from here we can say f alpha must be 0 and f dash alpha must also be 0. We need to find this limit, which is limit x tends to alpha fx upon f dash x greatest integral function of f dash x upon fx. Now we know that any greater function of x is always less than or equal to x, and it is strictly greater than x minus 1. So from here we can say this greatest integral function of f dash x upon fx will always be less than equal to f dash x upon fx, and will be strictly greater than f dash x upon fx minus 1. Now we need to multiply it with fx upon f dash x. So we multiply everything with fx upon f dash x. We can write this as fx upon f dash x into f dash x upon fx minus 1, it is less than fx upon f dash x into greater function of f dash x upon fx and less than equal to fx upon f dash x into f dash x upon fx. Now I'll cancel. Here this first part will cancel. So we'll get this as 1 minus fx upon f dash x is less than fx upon f dash x into greatest singular function of f dash x upon fx, that is less than or equal to 1. Now if we take this limit extends to alpha, then we can write this limit extends to alpha. Here also it will be this limit extends to alpha, and here also it will be this limit extends to alpha. So value of this limit on the right hand side, it is 1. We need to find value of this limit on the left hand side. Now this is 1 minus. Now what about this fx upon f dash x? Now if we know that f alpha is 0 and f dash alpha is 0, it means this alpha is double root of this function fx. So we can write this function fx as sum x minus alpha square into, and this f dash x will be sum x minus alpha into hx. So this fx upon f dash x will have x minus alpha and then some ratio of polynomials px upon qx. Now if we take this limit extends to alpha, here alpha minus alpha will be 0. So value of this limit is 0. So this expression will take the limiting value 0. So limit on the left hand side is also 1. Now limit on the right hand side is 1. Limit on the left hand side is also 1. Then from sandwich theorem we can say that this limit will be equal to 1. So answer to this limit is 1, and that's your option B. Now here the questions, we need to solve this limit, which is limit x tends to infinite. This is log x to the power n, which is n log x minus greatest new function of x upon greatest new function of x. Suppose this is limit L. Now this L is limit x tends to infinite. We write this as n log x upon greater function of x minus 1. Now we know that we can write greatest new function of x as limit x tends to infinite, and it will be n log x, and this is x minus fraction part of x minus 1, or we'll write this as limit x tends to infinite n log x upon x divided by 1 minus fraction part of x upon x minus 1. Now we'll solve these two limits. Limit x tends to infinite log x upon x, which is infinity upon infinity form. Now we use L'Hopital's rule. It will be this limit x tends to infinite, and this is 1 by x upon 1, which is 0. So this limit in the numerator will be 0, and we'll solve the second limit, which is limit x tends to infinite fraction part of x upon x. Now we know that fractional part of x will always lie between 0 and 1, and if we divide it with x, so it will be this fraction part of x upon x less than 1 by x. Now if we take this limit x tends to infinite, it will be this 0, and then limit x tends to infinite fraction part of x upon x, and will be 0. Then from sandwich theorem we can say that the value of this limit will also be 0. So answer to this limit is 0 minus 1, which is simply minus 1, and that's your option A. Now here the questions, we are given two statements. If we look at the statement 2, and statement 2 is limit x tends to infinite fractional part of x upon x, it is equal to 0. Now we know that any fractional part function will always lie between 0 and 1. Now if we divide everything with x, we can write fractional part of x upon x will be less than 1 by x. Now if we take this limit x tends to infinite, then limit of this function on the left hand side is 0 and limit of this function on the right hand side, which is 1 by infinite, is also 0. Then from sandwich theorem or squeeze play theorem, we can say that this limit x tends to infinite, fractional part of x upon x is equal to 0. That means this statement 2 is correct. Now if we look at this statement 1, then we are supposed to find this limit x tends to 0 positive x upon a and get a function of b by x. Now we can write this as limit x tends to 0 positive. This is x by a and we can write b by x minus fractional part of b by x. Now we can write this as b upon a minus this limit x tends to 0 and we can rearrange this as 1 upon a b by x and this is 1 by x. We'll multiply and divide with b also. Now when x tends to 0, 1 by x tends to infinite. Now this statement 2 says if x tends to infinite, then fractional part of x upon x, it is 0. So in that case, this limit will be 0. So value of this limit will be simply b by a. So this statement 1 is true, statement 2 is true, and statement 2 explains statement 1. Now here the question is, we need to solve this limit. Limit x tends to 0, x to the power 8 into greatest integral function of 1 by x cube. Now we know that greater function of x, it is always less than equal to x, but it is greater than x minus 1. So we can write greater function of 1 by x cube will be less than equal to 1 by x cube, but greater than 1 by x cube minus 1. Now we'll multiply it with x to the power 8. Now if we multiply it with x to the power 8, it will be x to the power 5 minus x to the power 8 and less than x to the power 8 into greatest function of 1 by x cube. It is less than equal to x to the power 5. Now if we take this limit x tends to 0, then in that case, this left hand side function limit is 0 and limit of the function on the right hand side is 0. Then using sandwich theorem, value of this limit, it must also be 0. So this is 0, which is a rational number and which is also an integer. So the correct options are B, C and D. Now with L'Hopital's rule, we use something called as Newton-Leibniz formula. Now, if we have a function which is written in terms of an integral, say this integral from f1x to f2x, and it is this function gt dt, and we want to differentiate this function, then we can simply write this as dy by dx equals, now here upper limit is f2x. So we'll put this upper limit here. So it will be this g f2x into derivative of upper limit. So into f2 dash x and then minus, in the same way, lower limit g f1x into derivative of f1x. Say for example, suppose we have this function fx, which is this integral from 1 by x to x square sin t square upon 1 plus t dt, where x is greater than 0. Now we have to differentiate this function. Now we can write this as f dash x. Now upper limit is x square. So wherever we have t, we'll replace it with x square. So it will be this sin x square whole square sin x to the power 4 upon 1 plus x square into derivative of x square, which is 2x minus, and then lower limit is 1 by x. So now we'll replace to the 1 by x. So it'll be this sine 1 by x whole square upon 1 plus 1 by x into derivative of 1 by x, and derivative of 1 by x is minus 1 upon x square. So whenever we have these integral functions with variable limits, we can differentiate these functions using Newton-Leibniz formula. Now we take another example. Say we have this y as a function of xs, this integral from 1 to x square log 1 plus t upon t dt. Now we have to differentiate this function. Now upper limit is x square, so we'll put this upper limit. So it'll be this log 1 plus x square upon x square into derivative of upper limit, and derivative of upper limit is 2x minus, and if we put 1, it'll be this log 2 upon 1, and then derivative constant is simply 0. So derivative of this function, it will be 2 log 1 plus x square upon x. Now we take a very simple example. It will be this limit x tends to 0, this integral from 0 to x to the power 4 sin t square dt upon x to the power 12. Now we put x as 0, this integral is from 0 to 0, which is 0, upon x is 0 is 0, so it is 0 upon 0 form. And if it is 0 upon 0 form, we can use L'Hopital's rule. Now in L'Hopital's rule, we have to differentiate the numerator and we have to differentiate the denominator. Now since we have this integral function in the numerator, we have to use Newton-Leibniz formula. So we can write this as this limit x tends to 0. Now if we differentiate this, upper limit is x to the power 4, which you want to put in this function. So it will be this sine x to the power 8 into derivative of upper limit, which is 4x cube minus, and since we have this constant here and derivative constant is 0, so it will be 0 upon 12 x to the power 11. Now this 3 and 11 will cancel, so we'll get this as x to the power 8. Now sin x to the power 8 upon x to the power 8, it is standard limit 0 upon 0 form, which is 1. So answer to this limit will be 4 upon 12, which is 1 by 3. So this is how we'll be using Newton-Leibniz formula in L'Hopital's rule to solve limits. Now here the question is, we'll need to find this limit x tends to pi by 4 integral from 2 to secant square x ft dt upon x square minus pi square upon 16. So we have this limit x tends to pi by 4, this integral from 2 to secant square x ft dt upon x square minus pi square by 16. Now we'll put x is pi by 4, secant square pi by 4 will be 2. So this integral will be from 2 to 2. So we have 0 in the numerator, and then in the denominator we'll have pi square by 16 minus pi square by 16. So it is 0 upon 0 form. And when it is 0 upon 0 form, we can use L'Hopital's rule. So we'll differentiate the numerator and we'll differentiate the denominator. So we'll write this as limit x tends to pi by 4. Now here we'll use Leibniz integral formula. So it'll be f secant square x into 2 secant x into secant x 10x. So it'll be 2 secant square x into 10x upon 2x. Now we can cancel this 2 with 2. Here 10x upon x, it is not 1 because this is not x tends to 0, it is x tends to pi by 4. So we'll put the value of x as pi by 4. So it'll be f. Now secant square pi by 4 is 2. This value is 2. 10 pi by 4 is 1. upon pi by 4. So value of this limit will be 8 upon pi f2, and that's your option A. Now here the question is, we are given this function f which is continuously differentiable such that f2 is 6 and f dash 2 is 1 by 48, and it says if this integral from 6 to fx 4t cube dt, it is equal to x minus 2 gx. We need to find this limit x tends to 2 gx. So from here we can write gx as this integral from 6 to fx 4 t cube dt upon x minus 2, and now we'll take this limit x tends to 2. Now we take limit x tends to 2, we'll get f2, and f2 is 6. So this integral will be from 6 to 6, which is 0, and then 2 minus 2 is 0. So this is 0 upon 0 form. And if it is 0 upon 0 form, we have to use L'Hopital's rule. So we can write this as limit x tends to 2. Now we'll differentiate the numerator using Leibniz integral rule. So it'll be 4 and then fx cube into f dash x minus, and here lower limit is constant. So derivative of lower limit will be 0 upon 1. So this limit x tends to 2 gx, it will be 4 f2 cube into f dash 2. Now this is 4. Now f2 is 6. So it will be 6 cube into f dash 2 is 1 by 48. So this is 12. This is 36 by 2. And this is 18. So value of this limit is 18, and that's your option A. Now here the question is, limit n tends to infinite n square, this integral from minus 1 by n to 1 by n 2006 sin x plus 2007 cos x into mod x dx. Now what we'll do is, we'll write this limit as limit n tends to infinite, this integral from minus 1 by n to plus 1 by n 2006 sin x into mod x dx plus minus 1 by n to plus 1 by n 2007 cos x mod x dx whole divided by 1 upon n square. Now this first function, it is an odd function, and if the limit is from minus a to plus a, then the value of this integral will be 0, and this function will be an even function. So we can write this as limit n tends to infinite to from 0 to 1 by n 2007 cos x, and then in this interval mod x will be simply x dx upon 1 by n square. Now if we put n tends to infinite, this is integral from 0 to 0, so it is 0, and 1 upon n square is also 0, so this is 0 upon 0 form. So we'll use L'Hopital's rule, and then where we'll differentiate numerator and denominator. So we'll write limit n tends to infinite to, and that will be 2007 cos 1 by n into 1 by n, and then derivative of 1 by n will be minus 1 by n square, and here in the denominator it will be minus 2 by n cube. Now minus and minus will cancel, 2 will also cancel, and n cube will also cancel. So we'll get this as limit n tends to infinite 2007 cos 1 by n, and it is cos 0, and cos 0 is 1. So value of this limit is 2007. Now here the question is, we need to find value of this limit. Limit x tends to 0, 1 upon x cube, this integral from 0 to x, t log 1 plus t upon t to the power 4 plus 4 dt. Now what we'll do is, we'll write this as this integral upon x cube. Now when x tends to 0, this limit will be from 0 to 0. So this is 0, and then in the denominator, it is also 0. So it is 0 upon 0 form. Now when it is 0 upon 0 form, we can use L'Hopital's rule. We'll differentiate the numerator. It will be x log 1 plus x upon x to the power 4 plus 4 upon 3x square. Now we'll cancel this x with x. Then we can write 1 by 3 into, I will put x as 0 here. We'll get 1 by 4. And then this limit x tends to 0 log 1 plus x upon x. And this is 1. So value of this limit is simply 1 by 12, and that's your option B. Now here the question is, evaluate this limit x tends to infinite, this integral from 0 to x e to the power x square dx whole square upon 0 to x e to the power 2x square into dx. Now I've taken this question from a standard textbook. So I think this question actually should be, we have to evaluate this limit x tends to infinite, this integral from 0 to x, and it should be e to the power t square dt whole square upon 0 to x e to the power 2x square dx. Now this is infinity upon infinity form. So we'll use Leibniz integral formula. We'll write limit n tends to infinity. This is 2 into integral 0 to x e to the power t square dt into derivative of this function will be e to the power x square into 1 minus 0. Then the denominator will be e to the power 2x square into 1. Now here e to the power x square and e to the power 2x square will cancel. So we'll get this as limit n tends to infinite. This is 2. This integral from 0 to x e to the power t square dt upon e to the power x square, which is infinity upon infinity form. Now again, we can use L'Hopital's rule. So we'll write limit x tends to infinite, it'll be 2, and then it'll be e to the power x square minus 0, and here it should be e to the power x square into 2x. Now e to the power x square will cancel. We'll get this as limit x tends to infinite 1 upon x, and 1 upon infinite is simply 0. So answer to this limit is 0. Now here the question is, let fx be a continuous odd function which vanishes exactly at 1 point. Now it is continuous odd function, and we know that for odd function f0 is 0 and f1 equals 1 by 2. That means this function, it will be in first and third quadrant with value at 0, 0, and at 1 this value is 1 by 2. Now we are given that capital Fx is this integral from minus 1 to x ft dt, and capital Gx is this integral from minus 1 to x t into mod of ft dt for all x belongs to minus 1 to 2. Now it is given that this limit x tends to 1 fx upon gx is 1 by 14. Now we'll write this as this limit x tends to 1, and then this integral from minus 1 to x ft dt upon this integral from minus 1 to x t into mod of f of ft dt, that is equal to 1 by 14. Now if we put x as 1, then limits of this integral will be from minus 1 to 1, and we know that fx is an odd function. So integral of an odd function from minus a to plus a will be simply 0. In the same way, this integral from minus 1 to 1 t into mod of f of ft dt. Now ft is odd, f of ft will be odd, but this mod sign, it makes an even function, and this t is odd, so this function is an odd function. So again, value this integral will be 0. So this is 0 upon 0 form. Now if it is 0 upon 0 form, we can use L'Hopital's rule. So if we differentiate this, we can write this as this limit x tends to 1 fx, and here will be this x into mod of f of fx, that is equal to 1 by 14. Now if we put x as 1, we write this as f1 upon mod of f1, that is equal to 1 by 14. Now in the question it is given that value of f1 is 1 by 2. So it will be this 1 by 2 upon mod of f1 by 2 will be equal to 1 by 14, or mod of f1 by 2 is equal to 7. Now since fx is positive when x is greater than 0, so we can write f1 by 2 is actually plus 7. Value of f1 by 2 is 7, and that is the answer to this question. And finally we'll have limit of sum. Now in limit of sum problems, we can change a limit into an integral. Now typically a limit of sum problem, it will have 3 characteristics. So we'll have this limit n tends to infinite, and then 1 by n, this summation where r varies from a to b, and this is f r by n. So if we have a limit which satisfies 3 conditions, first condition is the limit should be n tends to infinite. Second is wherever we have variable of summation, we should be able to express it in the form r by n. And third condition is it should have this 1 by n multiplied to this summation. So if any limit it satisfies all these 3 conditions, then we should know this problem is a problem of limit of sum. Now in limit of sum, what we do is we let r by n as x. In that case, this summation will change into integral. This 1 upon n, it will change into dx, and these limits, they'll change into lower limit, and lower limit will be this limit n tends to infinite. Now x is r by n, and lower limit of r is a. So it will be this n tends to infinite a by n, and its upper limit, it will be this limit n tends to infinite b by n, and this is say L1 and L2. We can write this limit as this integral from L1 to L2. Now r by n is x, so it will be this fx, and 1 upon n is dx. So answer to this limit is value of this integral. Now say for example, suppose it says find this limit. Limit n tends to infinite 1 to the power 100 plus 2 to the power 100 up to n to the power 100 upon n to the power 101. Now we can write this as this limit n tends to infinite, and this is summation r varies from 1 to n r to the power 100 upon n to the power 101. Now we can express this as this limit n tends to infinite. Now this is 1 by n, and then this summation r varies from 1 to n, and r by 100 upon n by 100 is r by n to the power 100. Now it satisfies all the three conditions. This is n tends to infinite. We have r by n and we also have 1 by n. We can write this as this integral. Now r by n is x, so it will be this x to the power 100 into dx. Now we need to write its lower limit and upper limit. Now its lower limit, say a, it will be this limit n tends to infinite. Lower limit of r is 1, so it will be this 1 by n and 1 upon infinite is 0. So lower limit is 0 and upper limit is this limit n tends to infinite r by n, and here upper limit of r is n. So this is 1. So it will be this integral from 0 to 1 x to the power 100. Now this is x to the power 101 upon 101 from 0 to 1. So answer to this limit will be 1 upon 101. Now here the question is, we are given this limit n tends to infinite. And we can write this numerator as this summation. R varies from 1 to n, r to the power 1 by 3. And this is n to the power 7 by 3 and plus this summation. R varies from 1 to n, 1 upon an plus r whole square. Now here we'll take n square common, so we can write this as this limit n tends to infinite. Now n square will cancel with n square, we'll get n to the power 1 by 3 and we'll take n to the power 1 by 3 with r to the power 1 by 3. So we can write this as this summation. R varies from 1 to n and will be this r by n to the power 1 by 3, and here will be this summation. R varies from 1 to n, that is 1 upon a plus r by n whole square. Now what we'll also do is we'll multiply numerator and denominator with 1 by n. Now it satisfies all the three conditions for limit of sum. Now we have n tends to infinite, we have 1 by n and we have r by n. So we'll replace r by n with x. So it will be this integral and then x to the power 1 by 3 dx. Now when r is 1, it is 1 by n and 1 by n is 1 by infinite 0 and upper limit is n by n, which is 1 upon, and for this also we can write this integral from 0 to 1 dx upon a plus x whole square, and it is given that it is equal to 54. Now it will be this x to the power 4 by 3 into 3 by 4 from 0 to 1, and here it will be minus 1 upon a plus x from 0 to 1, and it is equal to 54. Now this is 3 by 4 and here it is 1 upon a minus 1 upon a plus 1 and it will be equal to 54. Now this is 18. So we'll get a square plus a equals, which is 8 into 9. So it will be this a plus 9 into a minus 8 equals 0. So value of a is either minus 9 or value of a is 8. So the options are A and D. Now here the question is, for each positive integer n, let yn equals 1 upon n, and here we write this as this product r varies from 1 to n, n plus r whole to the power 1 by n. Now we'll take this n inside, so we can actually write this as yn, and it will be this product r varies from 1 to n, and this n upon n will be 1, and it will be 1 plus r by n whole to the power 1 by n. Now if we take log both sides, we can write log yn, and it will be this summation, because product will convert into sum. Summation r varies from 1 to n, and will be this 1 by n log 1 plus r by n. Now we need to find this limit n tends to infinite. So we'll take this limit n tends to infinite. That satisfies all the three conditions for limit of sum. It is n tends to infinite. We have 1 by n, and then we also have r by n. So we can actually write this as log yn will be equal to this integral log 1 plus x dx. So we'll change this 1 upon n as dx and r upon n as x, and then we'll change this summation into integral. Now when r is 1, x is 1 by n, 1 by infinity is 0, and when r is n, n upon n is 1. So it will be this integral from 0 to 1 log 1 plus x dx. So we'll write this as log yn, and this is 1 into log this. So we'll use by parts. So this is log 1 plus x into x minus this integral from 0 to 1, 1 upon 1 plus x into x dx. Now we'll put the limits from 0 to 1, and here we'll add 1 and subtract 1. So we can write log yn, and here will be this log 2 minus 0 and minus. Now this is from 0 to 1, 1 minus 1 upon 1 plus x dx. So it will be this log yn, and it will be log 2 minus 1 plus log 1 plus x from 0 to 1. So it will be this log yn, and will be 2 log 2 minus 1, which is log 4 upon e. So value of yn will be simply 4 by e. Now it says we need to find greatest integral function of this limiting value L. So greatest integral function of L will be greatest integral function of 4 upon e, and which is 4 upon 2.7 something, which is 1 point something. So value of this greatest integral function is 1, and that is the answer to this question. Now here the question is, we need to find the value of this limit, which is y, and limit n tends to infinite factorial n upon n to the power n to the power 3n cube plus 4 upon 4 n to the power 4 minus 1. Now what we'll do is, we'll write this as limit n tends to infinite, and we'll write it in terms of this product that r varies from 0 to n minus 1, n minus r upon n whole to the power, and here also we'll multiply and divide it with n. So it will be 3n to the power 4 plus 4n upon 4n to the power 4 minus 1 into 1 by n. Now what we'll do is, we'll take log both sides. So we'll write log y, and it will be equal to limit n tends to infinite 3n to the power 4 plus 4n upon 4n to the power 4 minus 1, and then into this 1 by n summation 1 minus r by n, where r varies from 0 to n minus 1. So we have this form. Now this is infinite limit. Highest power is n to the power 4. So this limit is going to be 3 by 4. So we can write this as log y equals 3 by 4, and then into this limit n tends to infinite 1 by n, this summation r varies from 0 to n minus 1, 1 minus r by n. Now here we'll take x as r by n, and this is nothing but this is limit of sum. N tends to infinite, we have 1 by n, and then we have this variable r by n. So it will be this log y equals 3 by 4, and we'll change it in integral form. Here will be this log 1 minus x dx and then this limit from 0 to 1, which is also same as 3 by 4, 0 to a minus x. So we can write this as log x dx. Now it will be this log y 3 by 4, and this is x log x minus x from 0 to 1. Now this is 3 by 4. Now log 1 is 0 minus this limit x tends to 0, x log x, and then minus 1. Now this is 0 into infinite limit, so we can write this as limit x tends to 0 log x upon 1 by x, which is 1 by x upon 1 by x square. So this limit is 0. So from here we can write log y equals minus 3 by 4, or value of y is e to the power minus 3 by 4. So value of this limit is e to the power minus 3 by 4. And that's your option A. Now for this question, we are given this function f and x, which is this summation. J varies from 1 to n, 10 inverse, and this is 1 plus x plus j into x plus j minus 1. And the numerator, we can write this one as x plus j minus x plus j minus 1 for all x belongs to 0 to infinite. Now this is 10 inverse x minus y upon 1 plus xy, which is 10 inverse x minus 10 inverse y. So we'll write this f and x as this summation. J varies from 1 to n, 10 inverse x plus j minus 10 inverse x plus j minus 1. Now if we put j as 1, it will be this 10 inverse x plus 1 minus 10 inverse x, plus if we put j as 2, it will be 10 inverse x plus 2 minus 10 inverse x plus 1, and will continue up to 10 inverse x plus n minus 10 inverse x plus n minus 1. Now here in this case, 10 inverse x plus 1 will cancel. So all these terms, they'll keep getting cancelled. So we'll have this term, and in the end we'll also have this term. So this f and x will actually be 10 inverse x plus n minus 10 inverse x, which we can also write as f and x, now 10 inverse n upon 1 plus x square plus nx. Now in the first option it says fj0. Now 0 is not included in the domain, so that means we cannot define f0 or f'0. So option A and B, they are definitely incorrect. Now we need to look at this limit x tends to infinite 10 f and x. So it will be this 10, and then this limit x tends to infinite, and f and x is 10 inverse n upon 1 plus x square plus nx. Now if x tends to infinite, it will be n upon infinite, which is 0, and 10 inverse 0 is 0. So answer to this limit will be 0. That means this option C is also incorrect. Now if we look at this option D, then in that case it will be this secant square, and then this limit x tends to infinite 10 inverse n upon 1 plus x square plus nx, and we know that this limit is 0, so it will be this secant square 0, and secant square 0 is 1. So that means the only correct option is this option D. Now here we are given that this function is defined from, now here the question is, if E denote the base of natural logarithm, then the value of real number A for which the right hand limit x tends to 0 positive 1 minus x to the power 1 by x minus e to the power minus 1 upon x to the power a is equal to a non-zero real number. Now we'll solve this question using expansion. So we'll use the expansion of 1 minus x to the power 1 by x. Now one of the way to find this expansion is using Maclaurin series, which we have covered in one of the previous videos. Now since we are assuming it's for JEE, we are not going to use Maclaurin series in this case. So what I'll do is I'll say, suppose this expansion is y, and we can write this as e to the power log 1 minus x to the power 1 by x, which is e to the power 1 by x log 1 minus x. Now we'll use the expansion of log 1 minus x. So it will be this e to the power 1 by x, and it is minus x square upon 2 minus x cube upon 3, so on and so forth. So it will be this e to the power minus 1 minus 1 by 2 x minus x square by 3. Now we'll take e to the power minus 1 common. We can write this as e to the power minus x by 2 minus x square by 3 up to infinite. Now this is expansion of e to the power minus x, and we know that expansion of e to the power minus x is 1 minus x, and x in this case is x by 2 plus x square by 3 and plus x square upon factorial 2. Now we are just concerned with first few powers. So in this case, if I take square of this series, then the term I'll get is x square upon, now this 4 and 2 will be this 8. So we'll get this as e to the power minus 1 minus x by 2, and then it'll be this minus x square by 3 plus x square by 8. So it'll be this minus 5x square by 24. Now we use this expansion to solve this limit. Now we put this expansion in this limit. We can write this limit as limit x tends to 0 positive, and here it will be e to the power minus 1 minus x by 2 minus 5x square by 24, and then minus e to the power minus 1 upon x to the power a. Now e to the power minus 1 will be cancelled. Now minimum power of x in the numerator is 1. So this limit will have a non-zero real number answer if the minimum power in the denominator is also 1. That means value of a must be 1 in this case. So the value of real number a, it must be 1, and if it is 1, then answer to this limit will be minus 1 upon 2e. Now here the question is, for any positive integer n, let Sn be defined as this summation k varies from 1 to n cot inverse of 1 plus k into k plus 1 x square upon x, and we'll write this x as k plus 1x minus kx. Now if we take its reciprocal, we can write it in terms of tan inverse, and it is tan inverse x minus tan inverse y. If we take its reciprocal, then we can write it in terms of tan inverse, and we know that tan inverse x minus y upon 1 plus xy, it is tan inverse k plus 1x minus tan inverse of kx. Now we'll simplify this summation. When k is 1, it will be tan inverse 2x minus tan inverse x plus tan inverse 3x minus tan inverse 2x, and we'll continue up to tan inverse n plus 1x minus tan inverse of nx. Now these terms, they'll cancel. Now since this second one here, in the end it will be this term. So we can write this Sn as tan inverse n plus 1x minus tan inverse of x, or we can write this as tan inverse nx upon 1 plus n plus 1 into x square. So that's a function Snx. Now domain of this function is from 0 to infinite to r.
Now in this first option it says S10x. Now for S10x we'll put n as 10. So it will be this 10 inverse of 10x upon 1 plus 11x square. Now we can write this as cot inverse of 1 plus 11x square upon 10x, and we know that cot inverse x is pi by 2 minus tan inverse x. So it will be pi by 2 minus tan inverse 1 plus 11x square upon 10x. That means this option A, it is correct. Now for this option B, we need to take this limit n tends to infinite cot, and then it will be this tan inverse, and since it is infinite limit, we look at highest power of n. In the numerator it is 1, in the denominator also it is 1. So answer to this question will be coefficients of n. So coefficient of n in the numerator is x and in the denominator is x square. Now we know that tan inverse 1 by x is cot inverse x and cot of cot inverse x is x. So this value will be x. Now for this C it says S3x equals pi by 4. Now what is S3x? Will be tan inverse of 3x upon 1 plus 4x square, and we put it equals to pi by 4. Now we can write this equation as 4x square minus 3x plus 1 equals 0. Now discriminant for this quadratic equation is 9 minus 16, which is less than 0. So this equation will have no real root. So C is incorrect. Now in part D it says tan of S and X is always less than equal to 1 by 2 for any n greater than equal to 1 and x greater than 0. Now what we'll do is we'll take this as some function y, and this y will be nx upon 1 plus n plus 1 x square. Now we'll find its absolute maxima and minima when x is greater than 0. Now we find dy by dx. dy by dx will be 1 plus n plus 1 x square into n minus nx into n plus 1 into 2x upon 1 plus n plus 1x whole square. Now here we'll take this n common, then we can write 1 plus n plus 1 x square, and here will be minus 2 n plus 1 x square upon 1 plus n plus 1 x whole square. Now we solve this, we'll get two critical points, plus or minus 1 upon under root of n plus 1. Now it will be minus 1 upon under root n plus 1 and plus 1 upon under root of n plus 1. Now we do not know anything when x is less than 0. So we are just concerned with this point. Now rightmost it is minus and then it is plus. So we'll have a local maxima when x is 1 upon under root of n plus 1. So this maximum value of y, it will be n upon under root of n plus 1 and 1 plus n plus 1, 1 upon n plus 1, so it will cancel. So it will be this n upon 2 under root of n plus 1. So the correct options are only A and B.
In this question, we are given these four functions and we need to find these two limits. Limits x tends to 1 and limit x tends to 0. Now, if we look at this first function, we are given fx is x into signum function of x minus 1. Now, we know that signum x minus 1 is minus 1 when x is less than 1. So, it will be this minus x. When x equal to 1, it will be 0. And when x is greater than 1, it will be plus x. Now, if we look at limit x tends to 0 fx, in that case, its definition is simply minus x, which is 0.
And if we look at limit x tends to 1 negative fx, it'll be this minus x, which is minus 1, and limit x tends to 1 positive fx, it will be this x, which is plus 1. So at x equal to 1, this limit does not exist. So for this first function, at 0, this limit is 0, but at 1, this limit does not exist. Now, if we look at this b, then we are given this function fx as sine of 10 x square by 2 upon log cos 3x. Now, if we take this limit x tends to 0 fx, it will be 0 upon 0 form, and if it is 0 upon 0 form, we can write limit x tends to 0. Now, this is cos of sine 10 x square by 2 into cos of 10 x square by 2 into secant square x square by 2 into 2x by 2, and here it will be log is 1 upon cos and cos is sine, so it will be minus 10 3x into 3. Now this is cos 0 is 1, cos 0 is again 1, secant 0 is 1, and here 2 and 2 will cancel. What we'll also do is we'll multiply and divide it with 3. Now this is 3x upon 10 3x, it will be 1. So this limit x tends to 0 fx will be minus 1 by 9. Now what about limit x tends to 1 fx? Now what about limit x tends to 1 fx? Now if we take limit x tends to 1, in that case it will be this sine of 10 square 1 by 2, and then it will be log cos 3, and cos 3 is less than 0. So in that case, this function itself is not defined. Now for this c, we are given this function fx as 1 plus 10 inverse 3x to the power 1 by 3 minus 1 minus sine inverse 3x to the power 1 by 3 upon 1 minus sine inverse 2x to the power 1 by 2 minus 1 plus 10 inverse 2x to the power 1 by 2. Now we look at this limit x tends to 1 fx. In that case, we'll have this sine inverse 3, and sine inverse 3 is not defined. So this limit x tends to 1, it doesn't make sense in case of this function. The only limit we have to calculate in this case is this limit x tends to 0 fx. So it will be this limit x tends to 0 fx. Now this limit, it will be this limit x tends to 0, and we'll use binomial expansion. So it will be this 1 plus 1 by 3 10 inverse 3x minus 1 minus 1 by 3 sine inverse 3x plus higher powers, and then it will be 1 minus 1 by 2 sine inverse 2x, and then minus 1 plus 1 by 2 10 inverse 2x. Now this 1 will cancel. We can write this as limit x tends to 0. Now this is 1 by 3 10 inverse 3x plus 1 by 3 sine inverse 3x plus higher powers of 10 inverse and sine inverse, and here will be minus 1 by 2 sine inverse 2x minus 1 by 2 10 inverse 2x and higher powers. Now we divide everything with x. This 10 inverse of 3x upon 3x is 1, sine inverse of 3x upon 3x is 1, again sine inverse of 2x upon 2x is 1, and 10 inverse of 2x upon 2x is 1, and all the high powers will be 0. So answer to this limit will be simply minus 1. And finally, we have this function fx equals e to the power 1 by x minus 1 e to the power 1 by x plus 1. So this d is fx is e to the power 1 by x minus 1 and e to the power 1 by x plus 1. Now limit x tends to 1, fx has no problem. In that case, it will be e minus 1 and e plus 1. But if we look at left hand limit at x equals 0, it will be limit x tends to 0 negative e to the power 1 by x minus 1 upon e to the power 1 by x plus 1. Now this is e to the power minus infinite and e to the power minus infinite is 0. Then in that case, it will be 0 minus 1 and 0 plus 1, which is minus 1. And in that case, right hand limit will be limit x tends to 0 positive e to the power 1 by x minus 1 e to the power 1 by x plus 1, which is infinity upon infinity form. So what we'll do is we'll divide everything with e to the power 1 by x. Then in that case, it will be 1 minus 0 and 1 plus 0, which is 1. So in that case, left hand limit and right hand limit, they are not equal. So this function fx limit x tends to 0, it does not exist. Now here the questions we are given. This function gx, which is x minus 1 to the power n upon log cos to the power m x minus 1 when x lies between 0 and 2, where m and n are integers and m is equal to 0 and n is greater than 0. Now p is left hand derivative of x minus 1 at x equals 1. Now if we look at this function, x minus 1 will be minus x plus 1 when x is less than 1, and it will be x minus 1 when x is greater than or equal to 1. So if we look at its left hand derivative, f dash 1 negative, it will be simply minus 1. So that means value of p is minus 1. Now it says limit x tends to 1 positive gx is p. So this limit x tends to 1 positive x minus 1 to the power n, and here we'll take this power out, so it will be m log cos x minus 1, and this is equal to minus 1. Now this is 0 upon 0 form. We'll use L'Hopital's rule. So it will be this limit x tends to 1 positive, and this is n x minus 1 to the power n minus 1, and this is m, and this is 1 upon cos, and cos is minus sign, so it will be minus 10 x minus 1, and this is equal to minus 1. Now this minus and minus will cancel. We can write this as limit x tends to 1 positive n x minus 1 to the power n minus 1 upon m 10 x minus 1. Now this limit, it must be equal to 1. Now we know that 10x upon x, it is 1. That means this x minus 1 to the power n minus 1, it should be actually x minus 1 to the power 1. So that means value of n is 2. If value of n is 2, this limit is 1. From here we get n equals m, and since m is 2, therefore m is also 2. So answer to this question is this option C, n equals to n, m equals 2. Now for the sixth question, we are given this function fx as 1 upon mod log x into 1 by x plus cos x. Now we can take this limit x tends to infinite fx, and it will be this limit x tends to infinite. Now when x is positive, mod log x is simply log x, so it will be 1 upon log x into x plus 1 upon log x into cos x. Now when x tends to infinite, log x tends to infinite, so it will be 1 upon infinite, which is 0, and here also it will be 1 upon infinite, which is 0, into cos infinite, which is oscillating value between minus 1 and 1. So value of this limit is 0. That means this statement 22, limit of fx does not exist when x tends to infinite, it is incorrect. Now what about this 21? As x approaches infinite, we have this term 1 upon log x into cos x. Now this cos x will oscillate between minus 1 and plus 1. So value of this function fx is going to oscillate when x tends to infinite. That means this statement 21 is correct. 23rd is
as x tends to 1, fx tends to infinite. Now if we take this limit, x tends to 1 upon mod log x 1 upon x plus cos x. Now it will be 1 upon mod log 1, and this is 1 plus cos 1. Now 1 plus cos 1 is positive. Now log 1 is 0, and basically this is 0 positive, and 1 upon 0 positive is plus infinite. That means this statement 23 is correct. And if we take this limit x tends to 0 positive, limit x tends to 0 positive fx, we'll have this as this limit x tends to 0 positive. Now when x is 0 positive, log x is negative, so it will be minus 1 upon log x 1 upon x plus cos x. Now log 0 is minus infinite, so this value will approach infinity. So this statement 24 is also incorrect. So the correct statements are 21 and 23. Now in question number 7, we are given that f0x is x, and for x greater than 0, we have defined this function inductively by fn plus 1 x equals x to the power f n x. So we have f1x as x to the power x, f2x as x to the power x to the power x, and f1 and f-10, it is 1. Now this first one is as x tends to 0 positive, f1x tends to 1. So we have defined this limit x tends to 0 positive, f1x, and f1x is x to the power x. So it will be this limit x tends to 0 positive, x to the power x, which is 0 to the power 0 form. Now we can write this as e to the power, this limit x tends to 0 positive, x log x, or this is e to the power limit x tends to 0 positive log x upon 1 by x, which is infinity upon infinity form. Now this is e to the power limit x tends to 0 positive. Using L'Hopital's rule, we'll have 1 by x and minus 1 upon x square, which is e to the power 0, and that is 1. That means statement 25 is correct. Now we look at this limit for 26, which is limit x tends to 0 positive, x to the power x. Now we can write this as this limit x tends to 0 positive, x to the power x. Now we know that this limit x tends to 0, x to the power x, it is 1. So it will be this value 0 to the power 1, and 0 to the power 1 is 0. That means statement 26 is incorrect. Now this 27th is this integral from 0 to 1 f3x dx, which is this integral from 0 to 1. Now f3x is x to the power x to the power x dx. Now if you look at this function f3x, it is x to the power x to the power x to the power x. X lies between 0 and 1. Now here x to the power x to the power x to the power x will always be less than or equal to 1. Now if we take this integral from 0 to 1, x to the power x to the power x to the power x to the power x dx, it will be less than this integral from 0 to 1 dx, as this function is not a constant function. Now this is 1. So value of this integral is always less than 1 and not equal to 1. That means this statement 27 is also incorrect. Now this 28 is derivative of f123 at x equals 1. Now here we are given that fn plus 1 x equals x to the power fnx. So basically yn plus 1, it is equal to x to the power yn, and if we take log and differentiate, we can write this as log y n plus 1, it is yn log x. Now it will be 1 upon yn plus 1 into yn plus 1 dash, it will be yn log x is 1 by x plus y dash n into log x. So basically derivative of f 1, 2, 3 at 1, it will be f 1, 2, 3 at 1 into f 1, 2, 2 at 1 into 1 plus f dash 1, 2, 2, 1 and log 1 is 0. Now any fn plus 1 x is 1 to the power 1 to the power 1 to the power 1. So this value will always be 1. So value of f1231 is 1 and f1221 is also 1. So value of this derivative will be 1. That means the statement 28 is correct. So the correct statements are 25 and 28.